So today we're going to be starting a new unit called solutions. So when we talk about solutions, a lot of times we're going to be talking about solutions with water. And water is sometimes referred to as a universal solvent. And water is called that because it is very versatile, because it is polar, if you guys remember, and it forms hydrogen bonds. So before we start, I do want to review that aspect of water, so make sure you write this down in your notes. So water, if you remember, the molecule is polar, so each water molecule, the oxygen end, which is represented by this red sphere here, is slightly negative, and the hydrogen end, represented by this white sphere, is slightly positive. And if you remember, the slightly positive hydrogen atom is slightly attracted to the slightly negative oxygen atom of neighboring water molecule. And this is called an intermolecular bond. Remember, that's between different molecules. So this is a hydrogen bond called a hydrogen bond. And this, like I said, makes water a very good solvent. So when we talk about substances in water, substances will either be hydrophilic, which means they're attracted to water molecules. So things that are also polar, like water, that have slightly positive, slightly negative ends, or ionic compounds will be very soluble in water, so they'll be hydrophilic. So that's why sodium chloride is very soluble in water. It's very hydrophilic. And things like sugar, which is polar, is also going to be hydrophilic. Now, other substances that are nonpolar will actually be repelled by water, and we call them hydrophobic. So wax, when you wax your car, is actually a very hydrophobic substance. So that's because it's very nonpolar, so it actually repels the water molecules. So after you wash your car, you will notice that the water, as it hits the car, kind of beads up on that waxy surface and doesn't really stick to the surface of your car very well. So when we talk about solutions, whether we're talking about something dissolved in water or something else, these are all homogeneous mixtures, if you remember, of two or more pure substances. And the solute is what is being dissolved, and that's going to be dispersed uniformly throughout the solvent, which is doing the dissolving. So we've been talking about water, but not all solutions will have water in them, and not all solutions will be a liquid with a solid in them. So some solutions can be gases, and air is an example of a solution. Some solutions can be in gas dissolved in a liquid, like we have oxygen dissolved in water, like in ponds. Salt, obviously, is a solid dissolved in water. We can also have solutions of different solids. If you remember, alloys are solutions. So these are all different types of solutions, but the ones we'll be focusing on will be typically water solutions. Now, solutions, I just want to go over some different properties of solutions. They have very small particles. So the particles in solutions will be anywhere from 0.1 to 1 nanometers. So you can't see the things that are dissolved. Because you can't see them, they are transparent. They do not separate. So you think about if you get vitamin water at the cafeteria, it doesn't separate after a while. It stays in solution. And this also means it cannot be filtered. Another thing we see with solutions is they do not scatter light. And we'll go over exactly what that looks like so you guys can see what that means. Now, solutions are different from something called colloids. So colloids, compared to solutions, have medium-sized particles. Their particles will be anywhere from 1 to 1,000 nanometers. But they can't be filtered, even though the particles are a little bit larger. But they can be separated with a very special type of membrane, which is a semi-permeable membrane. And this will almost look like a very thin sheet of plastic, but the holes in it are very, very, very tiny. And a lot of times they attract one thing better than another, and that's what makes them good at separating certain substances. And colloids will actually scatter light. So they have something called we see something called the Tyndall effect with them, which I'll show you guys a video to kind of illustrate that. So examples of colloids you might be familiar with are things like fog, whipped cream is actually a colloid, milk, cheese, blood plasma, and pearls. So those are all examples of colloids you might be familiar with. Suspensions are a little bit different from colloids and solutions in that the particles are larger. The particles here are greater than 1,000 nanometers. Suspensions can settle out. So example of a suspension is like if you get orange juice with pulp in it. If you let that sit for a while, you'll notice that the pulp kind of settles to the bottom. So before you drink the orange juice, you typically shake it to get it more mixed well so it doesn't taste kind of watery. That pulp in it can be filtered out, so you can get rid of it if you really wanted to. And like I said, you have to shake it or maybe stir it to help it stay suspended. Okay, so just some examples you might be familiar with for suspensions are things like blood platelets. Those will actually settle out. So a lot of times when you get blood, they'll have machines that will shake things up to keep it in suspension. Muddy water, if you think about if you see a pond when it's been raining a lot, initially the water will look really muddy, but if you come back a few days later, the surface of the water looks more clear and the mud has kind of settled to the bottom. Another thing is if you have poison ivy and use calamine lotion to treat that, before you use the calamine lotion, you have to kind of shake it up to get it back in suspension. So this is actually a picture of the Tyndall effect, and like I said, I'm going to show you guys a video. But here you can see light passing through. This is a true solution. You don't really see the path light makes through that. And then here is a colloid. You can very clearly see the path the light takes through that colloid. And this is just an example of the Tyndall effect. Think about if you're driving in a really foggy night or foggy morning, you might see like the light from your headlights kind of bounces back to you from the fog. And that's because a fog is actually colloids. The particles are large enough that they can scatter that light and it scatters it back into your eyes and makes it difficult for you to see the road. Okay, so I want to show you guys a video real quick illustrating the Tyndall effect to help you better understand that. So I'm going to pause this for a second and bring that up.
The Tyndall effect is a phenomenon where light scatters through a homogeneous mixture like a colloid or a very fine suspension, but it doesn't scatter through a homogeneous mixture like a solution. So this happens because the larger particles in a colloid or suspension scatter and reflect light, so the light's bouncing different ways, causing the beam to be big enough that it's actually visible to the naked eye. Think about like headlights passing through fog, right? You can see them, but only in fog where there's water particles suspended in the air. Now, this effect doesn't happen in a solution because the particles are actually too small. They're too finely distributed. And so the beam of light passes through the solution without being visible. So to illustrate this, I'm going to use a laser pointer. This is a laser pointer right here. And so we have 4 different substances. We have water, which is just a compound, H2O. We have vegetable oil, which is a solution. We have diluted milk. So I basically just took standard almond milk and then I diluted it with enough water so you can at least see the beam. So kind of making it like fog. And then also here I have flour, which I mixed in water. And this will be just a suspension. So I'll have to kind of shake it up a little bit too so you can see what's going on here. So I'm going to take the laser pointer and let's look at water. If you look at water, you'll see that you can kind of see the reflections on the glass, but other than that, you can't see the beam passing through it. Now for the vegetable oil, if you look at the vegetable oil, you can just barely see that beam passing through it. So, really not visible, and especially I have the lights down in here just so you can kind of see that beam. So not really that visible. Now we're going to take diluted milk, which is an actual colloid, and look at that. You can see that beam absolutely clearly. It's scattering enough of the light where that the beam actually becomes visible. And so then now here you have flour and water. So what I'm going to do is I'm going to kind of shake this up a little bit so you can see. So it mixes it. And then let me see if I can get this. Yeah, look at that. And you can actually see the particles in the actual water too. So those are the particles of flour that you're seeing. So just to compare the last two, this is a colloid. It's more evenly distributed than a suspension, but not as evenly distributed as a solution. And then right there, you can see the actual particles. So that is the Tyndall effect.
Okay, so now I want to go over what happens when something dissolves. So when we have something dissolve, we have a few things going on here. So in this picture here, I want you to visualize you have your solute. So when it's not in solution, the molecules or the ions in the solute are very attracted to each other. So you have to break apart those attractions. You have to break apart those solute-solute interactions to pull these further apart from each other to allow it to go into solution. You also have the solvent, which is also attracted to, these molecules are attracted to each other. So you have to break apart those interactions. So you have to break apart those solvent-solvent interactions. So both of these, you have to add energy for those to occur. So we represent that by a positive delta H. So you're adding heat, and that's how that's represented in chemistry. You also have the attraction between the solute and solvent. So this actually releases energy. So this is typically represented as a negative heat. So your energy is being released. So these three things have to occur for something to go into solution. So to summarize this, we have, like I said, the separation of the solute. So you have to overcome the intermolecular forces. That's what IMF stands for. Or another way to think about the ion-ion attractions in your solute. So like I said, this is endothermic. So we represent that as a positive heat. You're putting heat in. Separation of your solvent, you're also overcoming the intermolecular forces. Again, that's your IMF of your solvent particles. So this is also positive, it's endothermic, so you're adding heat. And then the attraction between the solute and solvent. So this is bonds that are intermolecular bonds that are forming between your solute and solvent. This is exothermic, so it releases heat. So we represent that by a negative delta H, so the heat's been going out of the system. Okay, when you have a solution forming, the three things that will affect how quickly something dissolves are things like your surface area, stirring your solution, and the temperature. So first, when you think about surface area, if you have a cube of sugar, one way to get the sugar to dissolve more quickly is to actually crush up that cube of sugar. And that's actually increasing the surface area of your sugar. And then that allows more contact between the water and the sugar. When you're stirring something, you're likewise increasing the amount of contact between your solvent and your solute. And that allows for more of your solute to go into solution. And finally, by increasing the temperature, the particles of your solvent are moving around faster. That allows them to come into contact with solute molecules more frequently. And then that will also increase how quickly the solute will go into solution. Now, some things you're going to find don't ever go into solution, and no matter what you do. So this has to do with like what you're dissolving, the nature of the solute or solvent, what temperature you're dissolving something at, and sometimes the pressure. So we're going to go over each one of these things. So what you're dissolving is very important. So there's two terms in chemistry that like dissolves like. So something like water is going to dissolve things that are polar, like sugar, or ionic, like sodium chloride, very well. So we say this water is polar, So it's going to dissolve things that are, like I said, that are also polar or ionic. So that's what it means by like dissolves like. Something that's nonpolar, like hexane, this is a very nonpolar molecule, just has carbon, hydrogen, very symmetrical. It's going to dissolve other things that are also nonpolar, like oil or grease. So if you ever have taken art class and use oil-based paints, you will find that if you try to go to the sink and wash off that oil-based paint with soap and water, you're going to put a lot of soap on it, a lot of water. Nothing's going to happen. It's just going to get more and more of a mess. But if you get turpentine, that is non-polar. That's going to take off the oil-based paint very quickly, and they'll get that off your hands. So that's an example of like dissolving. Like turpentine or hexane are very non-polar. They're going to dissolve things like oil and grease very well. So water won't work in that situation. So if you look at, so here we have something that's polar, ethanol. So it has the ability to do hydrogen bonds with water. So that would dissolve very, very well in water because water is polar. So here we have ethanol. Here you see here that the ethanol will form hydrogen bonds with itself and also with water. And that's why it's very soluble in water. So if we look here, we have two different molecules. This is glucose, which has a lot of polar components to it. So it will hydrogen bond with water very, very well. Cyclohexane is a very symmetrical molecule. It's very nonpolar. It will not dissolve in water at all. So this would need a nonpolar solvent to be able to dissolve. So here we have vitamin A, which is mostly nonpolar, has only a very small polar portion. We have vitamin C, which is mostly polar. So there's a lot of ability of vitamin C to do hydrogen bonding with water, not so much with vitamin A. So we see that vitamin A, because it's mostly nonpolar, it's going to be fat soluble in your body. Vitamin C, because it's mostly polar, is going to be water soluble in your body. And what you see in this case is that with vitamin A, you can only take certain amounts of vitamin A. If you take too much, it will actually be poisonous to you because it'll collect in your fat tissues in your body. It won't go away very easily. Vitamin C has very high levels that you can take because if you take too much, it just goes into your urine and you pee it out. So it's not such a big deal if you take too much vitamin C. Vitamin A, though, is poisonous if you take too much. Look at the same thing here. We see this molecule has a lot of polar portions for the size molecule. So this is going to be water soluble. Vitamin E has a lot of non-polar regions, very few polar regions. So it's going to be fat soluble. So also the ratio of the polar regions to non-polar regions will kind of give you an indication if it will be water soluble or not when we're talking about vitamins. Okay, things that affect gases in solution are pressure. So what we see and the mass of gases. So gases that have higher masses actually tend to be more soluble in water because if you remember the London dispersion force, there's greater London dispersion forces with these gases. So things like krypton have higher masses than things like nitrogen. So nitrogen will be a little bit less soluble in water than krypton or argon because of the, the lower molar mass, so fewer electrons in nitrogen as opposed to a higher molar mass and greater number of electrons in argon and krypton. So the more electrons, the higher the molar mass, the greater the London dispersion force, and the more soluble those gases will be in solution. And finally, the effect of temperature. So Things that like solids, higher temperatures, usually the solids will be more soluble. So we see that here with these different solids. So most of these are more soluble at higher temperatures. And that's because at higher temperatures we have more kinetic energy. So we have more motion of molecules, more collisions, more interactions between solute and solvent, and this makes it more soluble. Opposite happens with temperature with gases. So higher temperature, gases are moving around more. They have a greater ability to escape from the surface of the solution. So they're going to actually be less soluble at higher temperatures. So here we see solubility decreases as the temperature increases with gases. So this kind of makes sense. Like if you store your soft drinks, you want to store them in the refrigerator where it's cold to help the carbon dioxide stay in solution. And if you think about if you have if lakes get really, really hot in the summertime, a lot of times there's less oxygen dissolved in the water, and that makes it difficult for fish to breathe. And sometimes you have fish kills in the water because of that. So, solubility increases for solids with temperature, decreases with gases.